Now that we've seen the basic sine and cosine graphs and what they look like, let's look at some transformations of these sine and cosine graphs. Now, the first thing that we actually saw before is that really sine and cosine are really just horizontal shifts of one another, right? So I think I had written something like the cosine of t is really the sine of t plus pi over 2, because we could look at the cosine like it was just a sine graph that was shifted to the left pi over 2 units. And you can also look at the sine of t as if it's the cosine that was just shifted to the right pi over 2 units. Okay? And actually, from this relationship here, we can actually get a cofunction identity, right? The thing that we had called the cofunction identity when we had done the right triangle trig, I believe. If we remember that the cosine of t that cosine is an even function, that means that the cosine of t is actually equal to the cosine of negative t. So we know that the sine of t is really the cosine of the opposite of this thing. So the negative t minus pi over 2. But then if you distribute that negative sign, you get the cosine of negative t plus pi over 2, which you probably have seen written as the cosine of pi over 2 minus t. So what we know is that the sine of t is really the cosine of pi over 2 minus t. And this was just what we had called the cofunction identity. And in terms of a right triangle, it was very easy to see. It was just the idea that like the sine of 20 degrees was the same as the cosine of 70 degrees. The sine of 40 degrees was the same as the cosine of 50 degrees, because pi over 2 we thought of as 90 degrees. So if you know the sine of one angle, it's the same as the cosine of the complement of that angle, right? Which is just found by taking 90 minus the angle, right? So like the sine of 60 is the same as the cosine of 30, so on and so forth. So that's an important thing to remember, the cofunction identity. And then the other cofunction identity, which you can basically get from this one, would be that the cosine of t is the same as the sine of pi over 2 minus t, right? Those are your two cofunction identities. But they really are saying the same thing, right? The sine of one angle is the same as the cosine of its complement. But the nice thing is it doesn't just work for angles between 0 and 90, it works for all angles. So before we look at the PowerPoint for like the formal definitions and things like that, the nice thing to do is just to look at what the different transformations look like graphically. Okay, so what I did here is I wrote this general function y equals capital A times the sine of b times the quantity x minus h plus k. Okay, and I'm going to let these different values vary now. So the a value right now is set at 1, the b value is set at 1, the h value is set at 0, and the k value is set at 0. So start off with the most basic thing I think that you probably remember from when we did transformations, the k value. That's just some outside value that's being added or subtracted to the function. So what that's going to do is, as I alter k, it's going to shift the graph up if k is positive, and it's going to shift the graph down if k is negative. Okay, so that's all it's doing. You're just shifting the graph vertically k units up or down. Now h, if we remember that from our basic transformations that we had done earlier, that's going to be a horizontal shift. But the difference was that minus sign, right? So x minus h. So if I make h a positive, it's something like h minus 1. That moves it to the right. H minus 2, that moves it to the right again. H minus 3, that moves it to the right again. But if I make h negative now, that's like x minus a negative, so it's like x plus 1, that would move it to the left. X plus 2 would move it to the left again, X plus 3, move it to the left again. So then x plus 5, you're back there. And you can see now the starting point of the graph basically is at negative 5, 0, when h is negative 5. And then when I made it h equals positive 5, the starting point of the graph was basically 5, 0. Okay? So that was your horizontal shifts. Now, A and B are beautiful now to look at when we have sine and cosine graphs, because what A is normally, right, A, that value out front, that's normally your vertical stretch or compression. If A is bigger than 1, it's a vertical stretch. And now let's look how that looks on the trig graph. Now it's very easy to see. That's a vertical stretch, right? You're pulling it up and you're pulling it down when A is greater than 1, right? It gets really high and really low. But then when A is less than 1, right? Like when A is 0.9, it's compressing it. 0.6, 0.5, 0.4, 0.4, 0.3, 0.4, 0.3, 0.2, 0.1, right? That's a really compressed sine curve now. And I bring it back to 1, and now it's normal. Make it greater than 1, it's really stretched. Okay, so it's easy to see the vertical stretch and the compression. And then the B, which was the horizontal stretch and the horizontal compression, now again, now it's going to be clear the difference between the horizontal and the vertical stretch and compression. All right, so as I make B greater than 1, what happens? This thing is being compressed. It looks like a spring that's being compressed, right? I'm compressing a spring horizontally. I'm pushing it together. So when B is greater than 1, it becomes a horizontal compression. And then when B is less than 1, it's like the string is being stretched out. It's a horizontal stretch. Okay? So horizontal stretch when B is less than 1, horizontal compression when B is greater than 1. So you put all those 4 things together, and there's your 4 transformations. Outside of the reflections, right? The only ones I didn't look at here were the reflections, right? Like if you put a negative value out front, what does that do? Right? That was a reflection in the x-axis. And if you put a negative on the inside, that was a reflection in the y-axis.